Well, hi, good morning, and thank you for joining me in my shop on March 23rd. So the last video ended with something kind of blowing up. I guess that would be a good way of describing it. The part right there. So we're going to start, forget everything else, we're going to examine this part, and we're going to figure out what happened to it. I think we can all guess with a pretty good guess. I don't think it's really too mysterious. But we're going to take a look at it, look at where it is in the circuit. One of the things I'm curious about is that this thing shot smoke out about this far. It just under pressure. How's that happen? Where's that pressure come from? There's some other curious things to note in the video that I shot. So I'm going to play the end of yesterday's video where this thing explodes a couple of times in a row here, so you can look at it repeatedly a couple of times and watch for things like the pilot light, and frankly I'm going to be looking for them too, because I've only glanced at this video again. I didn't really study it. So the pilot light's doing something weird, and I think in the background you can even see the dim bulbs back here. I'm not sure they did anything. I'm curious about it too. So that's what's going to be on the video next, is a couple of replays of the explosion. Okay, rather than cut the piece right, chop it into the video here after I'm all done, I thought I'd put it on right now. We can watch it together, and we'll see what. Just 1 second here. There we go. We'll see. Okay, watch this. Happens quick. Watch. Meter was set wrong. The meter's now set right. Ooh. Okay, let's just watch it again. This time I'm going to watch the dim bulbs in the background. You know what? The dim bulbs are not switched on because I can see in the top left hand corner, I can see the switch that I control the dim bulbs with, and it's up. So we have full power being supplied to the radio here. Okay, let's just play it again. Okay, so down in here you can see the dim bulb flashing. You can see now the switch is off, so my hand must have gone up there and switched it off. I only left the power on for a couple of seconds. Let's watch again. Meter was set wrong. The meter's now set right. Ooh. So the interesting thing about that light is it flutters a bit just before the smoke comes out. Smoke comes out, the light gets brighter. That's curious. So we'll watch it one more time, and then you can watch this as many times as you like on your own video. We're going to watch it just one more time. Let me just back it up here. Meter was set wrong. The meter's now set right. Ooh. It really shoots the smoke out to the right under some kind of pressure there. Interesting. Okay, go back to the live shot here. Let's take a close look at this with the close-up camera. See what we can see. It's a black. Where's the camera? Where's my camera? I've lost track of one of my cameras here. Oh, here it is. Okay. It's over here where I was doing tube testing earlier. Okay. I'm going to stop just for a sec here and fix that camera properly. Okay, let's take a closer look at the capacitor. So it's this brown one right here. Oh, it's obviously split. You could see that without this camera. Now you can see the stuff was shooting out of it. The smoke was shooting out of these splits in it. Now, how big is this thing? Well, it's a great big square capacitor. So these look like gigantic mica capacitors, but they are not. They are just molded paper capacitors, molded into a square shape. I guess maybe that gives some advantage in the construction or the design of the capacitor itself, because most capacitors are tubular and they've been rolled, but not this one apparently. Okay, so that's just basically a wax capacitor in a case. That's what I think it is. And I wonder where it is in the circuit. One lead. Oh, well, that looks like a replacement. You see the little joint there. This looks like maybe a replaced capacitor. What about the other side? The other side is down onto a terminal, but it's kind of clunky looking soldering there. I don't want to say anything until I determine if that's me who did that, or that looks pretty clunky too. Did I do that? I haven't done anything in this radio yet. How could I have done it? Well, it's soldered up, but that just doesn't look like particularly good job. Is that a replaced resistor? Can't tell for sure. Well, there's some curious things going on here. That black wire. Yeah, I guess it's terminating right on this terminal here. For a minute I thought, oh, this black wire's just been trapped into all this stuff here. It's just passing by, but it's gotten trapped. But I don't think so. This is hard to see in here because it's very dark. No, it's not very dark, but it's not as bright as I might want it to be. Let's put more light on it here. Okay, so one lead, and this is going to one of the tube pins of this tube, and we can count the tube pin number is number 1. It's the number 1 pin. A large, well, we don't know what was in here originally, assuming this is a replacement. Once in a while, somebody will cut a wire, like you see the lead there, in order to perform a test. They'll cut the wire, separate the part, perform the test, and then, oh, nothing's wrong here, and they'll solder it back. That's possible too. That's what happened here. Pin 1 on, oh, wasn't that the rectifier tube? I think that's the rectifier tube, isn't it? 35, yeah, that's the rectifier tube. So it's hooked up to pin 1 on the rectifier tube. Pin 1 on a rectifier tube, eh? That's a 35Y4. Let's look in the book here. 35Y4. I don't know Y4. 35Y4. So pin number 1 is a heater pin, and you see this in the middle of the heater. There's a lead coming off and going up to terminal number 4. That's what powers the light. The pilot light gets its power from this tap on the heater. Now the tap is shown pictorially in the center. It's not in the center. The tap is positioned specifically to generate around 6 volts during normal operation. So with enough, it's designed to do this, so you can peel a little current away, throw it through the light bulb, and have it enter the heater partway down. It's designed for this purpose. It's a trick. Otherwise, it's very hard to power a low voltage light in these tubes with no finish the sentence, Jim. I can't finish the sentence. Oh no. Okay, we're going to look at the schematic. We're going to take a look at what that pin number 1 on that tube is doing according to the schematic. Okay, we're looking at the power supply, and here's the tube. There's the pin number 1, and it's not far to find a capacitor. In the schematic it shows it connected right onto the light practically, so there you are, right across the power line, which explains why it was able to fry up the way it did. Because pushing out here was a combination of Niagara Falls, some other waterfalls here in Ontario, and 3 nuclear plants pushing on this thing. No wonder they cooked this little guy up. So this is the reason why you want to put, you always want to change this capacitor if you find one. If it's a wax capacitor, or like the one that's in this radio, I think we're going to find that it's a paper capacitor in a plastic cover. Get rid of them. And then there are special capacitors made to sit in this position which won't do what this one just did. And by the way, in this case, this capacitor is past the on-off switch. So if you turn the radio off, the capacitor is off. It's not energized. In some radios, this capacitor appears ahead of the switch here. And why they did this, I don't know, but they do. So anytime you plug the radio in, the same capacitor is on. Doesn't matter what you do with the switch, the capacitor is sitting here and it's on. So that means a radio like this radio, had I, let's say, left that capacitor in for some reason and returned it to the owner and they're playing it, and sometime from now, who knows when, if the capacitor were here, just having the radio plugged in means it could start on fire. Now, is it going to burn your house down? Not very likely. But there's not much stopping the electricity here. There's just your house fuse or circuit breaker, a 30 amp circuit breaker. There's no way 30 amps is going to leak through this capacitor even if it's on fire. I don't think it would draw 30 amps. So yeah, there's a risk certainly if it's here. Now I'm going to show you the type of capacitor that should go in there, and I'm going to put it in because I'm going to have to replace it, obviously. Wow. And you know, I would have gone looking for this as a wax, as a paper wax, you know, tubular capacitor. I might have had a hard time spotting it because they've used an unusual type. Or was it replaced? Good question. Was it replaced? Well, I don't know. It looks like something was done with it. Let's cut it out and have a look at it. I think I'm just gonna put a clip lead on there. I think this is probably a replaced capacitor. Okay, I'm gonna have to. Wrong clip lead there. When I cut parts out, I like to leave a little nibbon of wire on the terminal so I can spot that little piece of wire and be reassured about where I'm putting the replacement. And that's what I've done here, but I also will put a clip lead in. There we are. Kind of oily. There's more to this than I thought. Usually don't have oil coming out of these kinds of things. Where did this capacitor come from? Maybe this is a, you know, if this is not original, who knows where it actually came from, what it was really intended for. Is it something special? Or what? And I can't say I've ever really seen one exactly like this. Like, this is very large. We're going to look at it under the close-up camera here. Yeah, this is not a cheap capacitor either. You know, you wouldn't want to put these in radios unless they're doing it for a good reason. Or is this the 1950s safety capacitor? And yeah, it's only safe up until 2020. We passed the best before date on it. Let's take a look under the other camera here. What's happened here? Okay, bear with me. I'm just a little confused about things. What am I seeing? Oh, I know. I'm looking at the movie film from previous. Oh, you know what? Okay, I gotta stop. Okay, let's take a look at this guy. Of course, I'll look right at the front and read what's on it here. Mica mold. So it's claiming it's a mica capacitor. Wow. It's got a patent date, 19 something. I have to clean this more to read it better. I think I'm going to do that. I'm going to clean it up just a little bit better. fact, I'm going to crack it open. I can always clean the top here later. Let's crack it open. Mica, really? That's an awfully large capacitor to be mica. And what was the value? The value, I'm going to peek. I'm peeking at the schematic. The value is 0.04. I just don't think this is a mica capacitor. I think they're lying. Oh, no, they can't be lying. I'm not going to lie. Okay, put your money down. I got a glance of it there. I'm putting down 1 loonie. That's a Canadian dollar. 1 loonie says it's paper. Here we go. It's paper. It's a paper capacitor. It's a paper capacitor. It is actually, it's tubular, and then it's been squashed and shoved into this case. And then they wrote, they called it mica. I gotta clean that. Mica what? Mica bull. Mica bull. Mica liar. Mica. I don't know. It's like buying an electric vehicle and finding out it's got a gas engine afterwards because the car was called electric car. This is just being destroyed. In case you haven't seen inside a capacitor, I'm going to switch cameras here because, you know, what is in a capacitor? Here's a chance to see one. All these tubular wax capacitors I'm replacing, an example of which is down here in the, an example of which is right in front of you in the radio. I don't even have to, you know, one of these is the same as this. So see, this is just rolled up. And then we take these apart if we can. This is a very, very thin sheet. This clear stuff. And then there's going to be a thin sheet of aluminum. 2 thin sheets of aluminum, very close together. They lay the 2 sheets. That's hard for me to show you without sheets. Give me some sheets. I need some sheets. Here, how can I demonstrate this? What they're doing. This is terrible. This isn't going to work. It's got writing all over it. Can't let that go. So we'll just use my hands. Okay, so you can lay 2 sheets, one on top of the other, so they're lined up on the edges. Or you could lay 2 sheets like this. What would happen is if you lay 2 sheets and then roll them all up, at one end you'll have the one sheet sticking out, and at the other end you have the other sheet sticking out. And that's how they get the 2 plates. The sheets are plates, and one sticks out this end and the other one sticks out that end. All this aluminum you see kind of smashed together here. Let's go back on the close-up camera, because I think you're going to see that these are not, you know, really precision sort of things. So now how do you make a connection? That's aluminum foil. How do you make a connection? You need a steel wire with copper coating or nickel coating or something. How do you make a connection? You ram some metal up against it. You ram some metal up against it. And you just have the wire. The wire's falling out here somewhere. I don't know where it went. Oh, here it is. You can actually see it. The connection survived. Let's look and see. I don't have to use my imagination here. How is this piece of wire connected to that aluminum? Is it soldered? It kind of looks like it, doesn't it? Yeah, it looks like they soldered it. So how do you solder to aluminum? I guess you use a special solder, and I'm pretty sure this is a blob of some kind of welding, maybe? I don't know how they do it. But that would be one side, all the sheets for one side, and the other side. That's how they make it. Now, I'm going to stop. I'm going to clean the surface, and we're going to read what it says. See what these liars are saying. Liars! Okay, let's look at this. This is some kind of international cover-up going on here. I'm going to take action. Get the RCMP, Royal Canadian Mounted Police, on the case here. Mica mold is what that says. Isn't that a little bit misleading, wouldn't you say? And there's some writing underneath. Brook. I didn't get it clean enough. Type 345. It's pretty fancy. What's that writing underneath there? I gotta clean this thing and see that. I wanna see what it says. The lying. Okay, let's try this, because I'm gonna have to file a police report about this for sure. Mica mold. Brooklyn, USA. Patent number and type 345. But nowhere do they say, like in brackets, psst, it's a paper capacitor. They don't say it anywhere. And I don't think there's any writing on the back. They'd put like a PS. No. Well, that's so, you know, the key thing is the size of this just doesn't make sense. The value of its capacitance doesn't make sense to be a mica. Mica capacitors aren't physically this large, and don't, at least not many. I suppose there are some, but not many. And the value, 0.04, that's out of the range of a mica capacitor. If I unpeeled this, by the way, this would be like a meter and a half of stuff wrapped up in here. There we go. That's how they did it back then. Okay, but now I'll show you what we got put in there. We're looking at the value, just grabbing one to show you what they look like. This type here. It'll say type X or type Y. This says X2 on it. And so there's different applications, you know, across the power line, and a few other different applications, and different sizes, of course. So that's what I'm going to put in there. Now the thing about these is they won't do what this one did. They just won't do it. They won't fry up. Why? I don't know. We have to smash one of these open and ponder what's inside it. I'm not about to do that. Okay, so we'll put this capacitor back in, and presto, we've changed a capacitor, and an important one. We just not quite in the nick of time, that's all. Okay, I think it might be a smart idea to start up this radio and make sure it works. So volume's up a little bit, it's plugged in. This meter's doing nothing. Just put it over there. Okay, so I put this right across the power line. If I did something really dumb, something bad would happen. But I have the dim bulb system, so if I wired in a short circuit, all that's going to happen are these the dim bulb lights will just come on. Oop. There we go, perfect. And I'm stepping back a little bit. No. Now, could this improve the performance of the radio? I don't think so, but let's see. So I have the auxiliary loop in there, powered by my outdoor antenna, so it's got the boost. And we're operating at 104 volts, which should be plenty. Okay, I thought I had the volume turned down. I had it turned right up. So very little volume coming out of here. Let's tune it around a bit. So this is a French station at 860. This is CBC, Canadian Broadcast Corporation. It's our public broadcaster in Canada. Volume. Okay, so starting with the 0, going up about half. That's very weak. The radio should be really blasted by now. And that's full. So still weak, for reasons not yet known. While we have it operating here, let me just check the B+ voltage. See what it is. I expect it to be around 100 to 110, something like that. We'll check it right across the filter capacitors here. Best don't want to make a short circuit while I'm doing this. I think I'm best here and here. Why did we get nothing? We got nothing at all. My meter not working. 300 volts, DC, positive, lead is positive. Let's try it again. Try it. Interesting, it makes that click, eh? There we are. So that's on the 300 volt scale. It's 90 volts. It's about 80 volts. It's about 110. So that's pretty typical for these radios. I'm only feeding it with 103. So you could derive as much as 160 volts by rectifying an ordinary 120 volt house current. The peak of the voltage is actually 169 volts. Peak, just peak, not peak to peak, peak I think. And you can capture that peak voltage with a rectifier and filter system. But the thing is, as soon as you begin drawing current off it, it'll go down. So 120 volts would be typical. If this probably would be there if this were a little higher. Radio's operating. I think it's operating the same as it was. For instance, if I take the booster out, and I don't want to do that. I've got it clipped in there. I'm going to leave it. I don't need to take it out and prove it. So the thing that I think is really curious is, when I took this capacitor apart, I didn't see anything wrong with it. I didn't see any burned areas. I didn't see anything. So I'm going to take this further apart. And we're going to take a look at that after my coffee break. A good and reasonable question at this point is there anything else ready to catch fire in this radio? And offhand, I don't think so, but I do have a thermal viewer, and I can take a look at it and see if anything else stands out. Now, the way this works, as you might imagine, hot things appear red. What's that? Wow, what's all that? It's probably because of the settings. So I'm going to change the settings. You can control, what temperature things turn red. So as you might imagine, blue, green, yellow, orange, red is the temperature gradient as it's shown here. You can see it up the side. So let's set this. Right now, 25 degrees turns red. That's no good. We don't want that. We want this to be more like 40 degrees or something like that. 45. So what we're almost certainly looking at here are the two tube bases sitting right there. I can get up close to them. Come across. Notice the other two bases don't display heat. That's pretty interesting, eh? I think it's interesting. Why these two? Well, this is the rectifier, and this is the output tube, and they're both designed to run hot. Hot isn't. They don't really run at a higher temperature, I don't think. There's more filament in there. There's more heat production going on. There's more heat to cast off, and consequently, the temperature of things is going up higher. So, if we look right at the tube glass here, we might see the same effect. Now, can you see that? You can kind of see. I'll tip it a bit. So coming across. Oh, red. Oh, three red. So these two, they look kind of purple in the camera there, don't they? But they're red in my eye. Well, those are the two hot tubes that come out. There's another one here. That's the detector tube. And very, very cool. The other one, that's kind of surprising. But what about components? So now we've knocked the tubes out of the picture. Anything else? So right in here, that's another tube socket. That's another tube socket there. There's nothing heating up in here. Nothing is heating up. Wait a minute. Oh, that's a pretty complicated image. There's something down here running at 50 degrees C. Down in here. what I see down there is a resistor. Let me put the temperature up even higher here. I think we can kind of sharpen the image that way a little bit. It's kind of running on an angle like, you know what, it's got to be that resistor right there, I think. No, maybe not. I think it's immaterial anyway. Of course, some things are intended to run a little warm. It's possible it's this capacitor here. So what I can do is I can do heat blocking. So take something cool, put something there, and then bring this down. Watch what happens to the image here. See, as I heat block it. So we can kind of do this kind of thing. So, because it's hard to tell what you're seeing in this camera. The camera is very wide angle. It just makes it very, very difficult. So I hold this still, and I'll block out the. Hold it still. Don't get a shock. Okay, first thing you know, I can block this out and then pull the block away. That's even easier. Nothing. It's something up higher. Oh, well, how do you like that? So there's a resistor tucked down under here. And I think there's just so much heat in the area. And then it's blocked by the capacitor itself. And this wire here is blocking the view of the camera. Same way I'm having trouble seeing it. Oh yeah. Okay, so smart me. Line myself up so I can see it with my eyes and then put this thing in line, and there it is. So it's quite a hot resistor under there. How hot? How hot is it? Okay, so I can do that. It's around 60 degrees. On this device, you can see the big white number there. That's telling you the temperature of the dead center. There's a little plus mark. So anything that's under that plus mark, the temperature shows up here. So if I aim it so the red thing goes under the plus mark, which is not easy to do, the temperature of that red thing is 70, 68, 70. That's hot. The tube base. Now I got the radio tipped on this angle, so the heat is going to be, the hot air is going to be moving up this way. The heat is being conducted down through the tube. Yeah, these metal pins, which must be conducting the heat away a little better than the plastic. The classic tube with the plastic key. This has a metal key. And this radio's been on for quite a while now, so if something's going to overheat, it would have done it. Famous last words. What's over here? That's got a bit of heat. It's the tube socket. Okay, enough of that. Nothing seriously going on here. One resistor that's fairly warm, and I'm willing to bet that's the cathode resistor of the output tube. It's a fairly large resistor. I will show it to you with the other camera. In case you got the same radio and you're watching this because you are interested. See down under there, see the orange? It's kind of a, that looks like a capacitor. That looks like a molded capacitor. Okay, just don't want to stick this camera in so far I get a shock. Well, if this is a capacitor, it should not be getting warm. Or it's on its way like the other one. Wow. Okay, what capacitor is this? So it's connecting. So this is the power switch, back of the power switch. I better be careful with this camera. I don't shove it right in there because the radio is switched on. And why am I doing this with the radio switched on? No reason. Radio's off. No reason anymore. So that wire is going to this capacitor or resistor. I think it's a capacitor. And indications are it's getting hot. Now look at this other wax capacitor, this one here. Look at the end of it. Can you see? It looks like it's popping out. Look like a plug coming out of it. That's exactly what's happening. The wax is coming out. You notice the surface of the capacitor looks pretty dry too. It doesn't look all waxy and goopy. These capacitors look goopy when they're in good shape. Any goopy ones in here? Here's one. This one's goopy. It's covered in wax, you can tell. This one, not at all. Well, I don't think the wax disappeared from this. This guy's similar in a way, not really waxy on the outside. Got this end cap plug, but you see the wire itself can kind of open up an opening there. What would that opening be? That would be an opening for moisture to get in. The purpose of the wax is to keep the moisture out. The moisture goes in there, and before you know it, it'll conduct electricity the way it should not. Here's another one that's quite waxed up. Might just be differences in manufacturers. But this one, see, this one's really covered. Oh, the end looks a little roughed up. Very roughed up. So, getting back to where we were. Where were we? Yes, we were looking at this resistor capacitor thing. We got to figure out what that is. And then doubtful that the test I took was correct. So it's connected right to one side, the radio side of the switch, because here's the power wire coming in to the switch. And then it clicks through the switch, and then on the other side you would encounter, there's a couple capacitors here. One, hey, somebody wrote something. Blue. Well, that's a blue wire. Somebody's been in here. I don't think that would be done by the manufacturer. Way under there. And where is it connecting over here? What's going on there? So the two terminals that are in view now, I'm trying to understand if they're actually connected together. Sure looks like it. Gotta be. When you find terminals connected together, that's sometimes indicating it's really all grounded somehow. What's going on here? Oh, it's going to a different terminal. Okay. For a minute I thought this capacitor was just in parallel with this maybe capacitor here. Well, it's a little tough to figure this guy out. Maybe it's coming off the switch and heading to this terminal, which we don't really know what the business is of this terminal. There's a resistor there, and you can see it's that would be 47. That would be 470. So we look for a capacitor off the power line that's tied to a resistor. There's another resistor under there. Oh, I'm looking right at it, didn't even see it. Just buried under there. Holy smokes. But that's not of interest. The one that's of interest is this one. They're all of interest. 470K. Okay, enough of that. Let's take a look at the schematic here. And what we are looking for is coming off the on-off switch. Here it is. Wait a minute. This is the one I changed. Something bad has happened here. Is there a chance in the parts list, way down here, that there's some description of this particular capacitor? Oh, here they're giving the function here. Very good. Tone compensation. So which resistor, capacitor, 0.01, 0.02. Oh, they've done it by sections. Stuff in the audio circuits. Oh, very interesting how they've done this. This is a very interesting service manual here. We've got a whole pile of condensers coming down here. Am I ever going to be able to sort out? Fantastic. They're all named. Their function is all given. Thank you, Mr. Engineer, for taking the time to do that. A lot of this information, I don't think it would be of great interest to your average radio repair guy. He's just looking for the part that obviously burned. Huh. Okay, well, I don't think this is going to work. I don't think I'm going to be able to spot it this way. We go back to the schematic here. It was C100. What does it say about C100? Does it say something in C1, 1, C1? Hey, where? What happened there? Is there another page? No. C100. There's no doubt. 0.04. 0.04. 0.04. 0.02. Tuning condenser. 47 picofarads. Oh, you know why I'm not going to find this? That's a replacement capacitor. What does that matter? It doesn't matter. It doesn't matter. There's no point. There's no point. No 0.04 in here. Hey, I may have put in the wrong size capacitor there. I may have put it in the wrong place. I got things are not adding up here. This is not adding up. Any hint here? Well, okay, confusion abounds. How did I determine that other burned up capacitor was this one? How did I reach that conclusion? Because I saw it on pin 1. And it's all alone on pin 1. I got the pins wrong. It's pin 8. Okay, so the other, I didn't get the pins wrong. How does this work? Something funny going on here. Yeah, something funny going on. I'm going to stop for a bit. Okay, let's sort a couple things out here. The capacitor I put in is supposedly, I thought, across the power line. So I'm going to measure the resistance from the terminals of the capacitor to the power line, and we'll see. In fact, I can see right now this is connected right to the power line here. There's no question. So it's the other side. Is the other side connected to the power line? So watching the meter here. Be here, I guess, or here. There we go. Is that right to a 0? So that's past the switch. There must be a wire connecting one way or another right over to here. So there we are. In fact, I can see it. I can see the wire. The black wire from here and then a yellow wire right up onto the terminal. So this capacitor is definitely across the power line. Now, what about this other one? How did I come to the conclusion it was across the power line? I think I came to the wrong conclusion. I can see one lead of this is down here. This, I think, really represents B minus at this point. You should think of it that way. I think. I could be wrong. And so it's just a capacitor to B minus coming from this terminal, which is terminal number 1, 2. Terminal 2 on the output capacitor. Let's take a look at that. Did I say output capacitor? Output tube. Terminal 2. So here's 2. And here we see the capacitor. A capacitor. This is the one for sure. 0.02. And it's going, there you are. Right. We don't know for sure what's happening here. Right to the switch or the incoming power. So that's what that. So that the one I thought was across the power line, that confusion, is this one. This guy's pretty important. You know, he's sitting with B plus pushing on him here, about 100 volts pushing on it, and if it's faulty, it's going to carry current down to here. Now, what about that resistor? I was so interested in. I will figure that one out too. So I'm switching. So that would be pin number 1, 2, 3, 4, 5, 6. Pin 6 has this resistor attached to it. Let's take a look. Pin 6 here. Whoops. I'll zoom in a bit. So here's pin 6. And whoa. Okay, is that what that is? So C200 looks like a large molded capacitor. C200. Where's that number again? I've lost myself. CC200. C200. So let's C200. C200. C200 condenser DC blocking 0.01. Nothing special said here, except it's a DC blocking capacitor, which is what it's doing. Up here, it's the plate here has got 96 volts on it, and I'll take that back. This is not a blocking capacitor. Oh, I'm over here. Oh, crying out loud! You know what? Something wrong with me today. No more than usual. Here we are. So yeah, so it's blocking the plate voltage from here. 45 volts can't get over here onto the grid. That's right, and I was about to make measurements of the grid potentials here when the conflagration took place, and get back to that in a moment, now that I'm settled out on what this is. Yeah, let's go back and do that. We'll go after this capacitor, which, according to my temperature thing, it suggested it was warm. Not very likely, because even if this is shorted out, it's facing a large resistor here, so you can't get much current coming down through here. But we'll make these measurements: voltage on pin 6 and voltage on pin 7. Pin 7 will show us the proper bias voltage if this resistor is okay, and pin 6 should show us 0 volts to this, down to B minus here. Yeah, we'll work. Yeah, okay. Okay, so here's what we're going to do. We're going to go after this capacitor and replace it. And then we're going to perform tests based, or to try to determine the condition of this one. And then we would change it and then re-perform the test. And that should be enough for today. We'll start with changing out this guy. I don't think I'm going to test the radio. So what is this capacitor doing here anyway? It's going from the plate basically to the B minus, or ground if you like, and it's more or less so. I was going to say it's across this, but it's not quite across this, but nevertheless it's on the same circuit going to the output transformer. And the purpose of this guy is to catch and destroy high harmonics that may have been developed by the signal passing through these tubes. This is a pretty simple circuit. I'm sure it's got non-linearities in it, and you have a non-linear amplifier, you get harmonics, and that's almost certainly what's coming, particularly if I don't know, super loud signal or something. Anyway, some harmonics can be developed, and you're not going to hear them, but it's good to get rid of them rather than pass them through the transformer here and have them wasting energy or something like that. So they put a capacitor here to quell the harmonics. If this capacitor is too large, you would lose treble, I think. I don't know how large it would have to be, but you don't want to change the size of this. Should stick with the size that's here, 0.02. Okay, let's deal with that. Okay, let me cut it right out of here. So I guess if this capacitor is lacking capacitance, then it would not do its job, and we would have harmonics coming out, and I'm not sure that you would hear them or not. This is a pretty waxy capacitor. It looks pretty sealed. Oh, it doesn't look so good right up in here. Let's give it a test. I mentioned this on my video recently, but this clip lead is about to give out. So in the middle of doing this, I may have to stop and repair this. It's hanging by a thread here, hanging by one strand of wire. But maybe we can get away with doing this test. I can fix it later. Good. Okay. So what we're going to do is put, I think I've explained this. Have I explained this? I may not have explained this on this series of videos, so I will do that anyway. So this is a two-part device. It'll measure capacitance with this control if you wish, or it'll reveal the amount of leakage in a capacitor like this by putting a high voltage across the capacitor and then looking at how much current leaks through it, the high DC voltage across the capacitor. The first voltage not that high, 50 volts where I have this set. So when I operate the switch, 50 volts will go on the capacitor. You'll see this eye close. The eye is indicating current flow. More current flow, more closed the eye. And this is very sensitive, so a tiny amount of current will close this eye. And a tiny amount of current leaking through this capacitor is a sign of failure. There shouldn't really be any leakage through it at all. We're going to find out. So when I close this, what I expect to have happen is a charging current will go in the capacitor, the eye will close during the current flow, and then it will pop open to some degree or no degree or completely like you see it now. Here we go. So it opened right up. That tells me this is a good capacitor. Okay, so I'm 150 volts. It's only opening about halfway. So it's not like new. You put a new capacitor on here. I like to do this once in a while, keep myself honest, and to check the machine that it's still one little tiny wire holding it. So that's a brand new capacitor I've hooked up there. And then you watch the eye, we'll start at 150 volts. See it pop open, 250, 350, 450, and pop right open. So a perfectly good brand new capacitor does that. Old capacitors, not many of them can make it past 150 volts on this device without the eye closing significantly. And many of them, 50 volts, eye closed. Not necessarily from this radio, but. And by the way, when you let go of this switch, it puts a short on here to drain out the capacitor so you don't charge them up and then, walk around and hand them to your cat or something like that. So the result is not the worst. It's in a position where in the radio circuit where a little bit of leakage wouldn't really do anything. I don't think. Probably fine. Probably could have left it in there. But the only way to know is to take these out and test them. It's the only way to find out. So I'm going to put the new one in, and then we're going to examine the grid blocking capacitor. Very, very important capacitor in a radio like this. Okay, got that capacitor in right there. Now, I'm going to be taking some voltage readings in here while it's operating, so I just want to practice a little bit. Sounds kind of weird, but I'm going to clip the ground to a good B- point. There we go. Now I'm going to practice. So I want to touch the, what do I want to touch? I want to touch the grid. Right, and that's what this grid blocking capacitor is doing. You know what, this doesn't make sense. That's not a grid blocking. This is. How can that be the grid blocking capacitor? And the lead. Every time I think I got it figured out, I turn around, it doesn't look like it. Well, this is more likely the grid blocking capacitor here. It's coming from this tube, which is the mixer tube with the triode in it, and it's heading over to the output tube. This has got to be it here. But coincidentally, on the same terminal is this other thing going to the power line. We're going to look at the schematic again. So this is 876. Pin 6, it looks like pin 6 and pin 7 are tied together. pin 6. Capacitor, so pin 6 would be the grid if it's the signal coming through this way. Pin 6. Let's look. Pin 6, yeah, pin 6 is the grid. So this might be the guy. 330 picofarads. This might be the guy that's buried deep, and the one I was pointing out running between tubes would be this one. That's got to be what's happening. 330 picofarads, and it looks like a molded capacitor. Okay, we're just going to leave that one for now. We're going to focus on what I'm pretty sure is this one here. Okay, so I think I'm ready to do the test. Read the voltage here and the voltage here and make conclusions from that. I guess when it comes to conclusions, you don't make them. You draw conclusions. Okay, practicing again then. Grid and cathode. Maybe that's a cathode resistor now. I don't know. Cathode on, was it 6 and 7? I'm going to have to look again. 1, 2, 3, 4, 5, 6. 6 and 7? 6 and 7? Was it 6 and 7? Just bear with me a second. Where am I? 6 and 7. 6 and 7. 6 and 7 are the guys. Okay. I think we're ready for all that. Voltmeter, no, not resistance. We're looking for fairly low voltages. Fairly low voltages. 5, 10 volts, something like that. Ready to turn the radio on. Okay, here we go. Oh, here we go. There we go. The bulb came on briefly. What does the meter do? That was interesting. Come on, radio. There it comes. Okay, we should, if things are working right, we should see 0 volts on the grid. This might make a click on the speaker. Not much. We see a positive voltage of 1.6 volts. And we look on the cathode. Positive voltage of 8 volts. That sounds probably correct. So 8 volts is the, and you know what? Are we on full? We're not on full here. We need the full. Give her the full. Repeat the test. 1.8 positive on the grid. Ooh, wrong way. 9 volts of bias. Just getting a little bit of time there. So when I first put the meter on, watch the reading. Watch it now. That didn't really work well. Was it a little higher? 1.9? Let's go again. 2. It's going up slowly. That's interesting. I don't like the look of that. The other side of the capacitor over here should have 45 volts or something. Was that 45 or was it 90? I think it was 90. 45, 48. So that's the plate voltage. I think that's correct. And some of it is making it through that capacitor over to here. 2.8. This is bad news. What's happening here? This is very bad news. Well, it's easy to fix. Okay. And we go back to look at the cathode. Ooh, don't short them out, man. It's gone up a little bit too. Maybe the general voltages are going up over time as things get warmer and all that kind of stuff. Okay, so the objective now is to replace this capacitor and then see that voltage that was there, the 2 or 3 volts rising, becomes 0. That's the objective. Actually, my first objective is go drink some more coffee. Why not? So this is a really good opportunity to calibrate the my capacitor checker, because here is a capacitor that certainly isn't doing its job. We know the circumstances of it completely. So when I do the test, what am I looking for here? I'm looking for a clip lead. When I do the test, I can have a reasonable, it will help me calibrate the results that you see on the uncalibrated capacitor checker. Well, I've done hundreds and hundreds and hundreds of these now. Okay, making sure we're unplugged here before I stick my cutters right in there. It's so easy to be fooled by the wires and where you think they're running. Clip lead here. Because a lot of things are blocked from view. There's stuff over top of stuff, and things happen out of your view. Wires cross over each other, you don't see it. So here we are. So this one, 0.01. And you can see the end of it is popping out. Let's find out. Now if you notice, I'm not attempting to read the capacitive value of these capacitors. Once they become leaky, the test results are false if you attempt it. And we finally had it. It's my clip lead has failed. Okay, I gotta find a new solution here for this. I guess doing these little repairs all part of the picture. Hey, soldering iron. Burn your fingers. When you're soldering stuff, things can start out stiff with cold solder, and then at some point the solder melts, and all of a sudden the stiffness goes, and so does your project. This will get me through a few more tests, pretty sure. There we go. Very good. Let's go back here. Put this guy in. There we are. Look at that. And good to go again. Here's the capacitor in question. Just close my shop door here. Okay, keeping an eye on the eye. 50 volts. What do you do? So it's opened up about halfway. So it's actually not all that good, this capacitor. There, it's not going to open at all at 150. So I personally believe what is happening to these capacitors is moisture is penetrating them, and the moisture, water is contaminated water anyway. There'd be a little bit of ionic material left inside the capacitor and the paper and things like that that just couldn't be removed during manufacture, and then you throw a little moisture in there, and next thing you know you got one of these happening. Okay, so I'm going to put the replacement capacitor in, and then we will perform the after tests. See if it really did what I'm thinking it's going to do. Okay, got the grid blocking capacitor, and it's an orange one down in there. But my shop is full of smoke again, so I'm leaving for a bit. Okay, capacitor's in. Time for another test. find out if I have egg on my face. So we'll put this on the 60 volt scale. There you are. We're still tied to the B minus here. I'm ready to go like this. And I'm going like that and like that. That's right. So here we go. Are we all set? No. Gotta plug it in. The mysterious light came on. Okay, powering it up. Volume down is this way. Yeah. Volume up just a bit. Okay, here we go. Dim bulbs did the right thing. We're in business here. We're going to look for, first of all, the grid voltage. The grid voltage should be 0. It was 2 or 3 volts climbing before. Okay, full voltage too. We need the get what that works. By the way, that scratchy sound from the volume control. While this radio was operating before the conflagration, there was 2 or 3 times where the radio made a scratchy sound and then just stopped. And that was probably that capacitor working its way to its own doom. And of course, you can't tell what's making a sound like that. I often attribute it to the vacuum tubes warming up and the pins shifting in the sockets from the expansion. But I don't know. Okay, here we go. Uh-oh. No, we're not going anywhere. The radio has fallen silent. Jimmy, what did you do? What have you done? Okay, quick checks. B plus still there? Yes. And cathode voltage 8.2. I hear something in this radio now. More scratchy sounds. Somebody else getting ready to let loose. And the voltage on the grid. Well, that's a different effect, eh? Jim, what did you do? What stupid thing did you do? I've done something stupid. I think I've hooked this. Oh, how stupid can you get? I've hooked the capacitor totally wrong place. How did I manage that? Skill. Tremendous skill. How did I? Okay, I did. Anyway, yeah. I'm so used to making mistakes, I am constantly suspicious that anything that goes wrong is because I've made a mistake. And it's true. Okay, time for another test. Let's give this guy a chance. I think I fixed my error. Just neatening up here a bit before powering up. Plug it back in. Okay, here we go. Dim bulbs normal. Volume is, I think it was way up. Whew, patience. More cracking. Ooh, what the heck is that? Shh, don't make these sounds. Well, am I really messing this up today? Okay, B plus on the tube ahead, 45 volts, that's correct. B plus on the other side of the capacitor should be nothing. Did I? feeling I'm really clued out here. What's happening? Yeah, it's not coming to mind. Okay, I'm going to stop for a bit here because this is going wrong in too many directions at once. So I'm going to stop for now. And you know what? It's lunchtime. You know, eat lunch and then look at this after lunch again. So I think what I'm going to do is I'm going to give this radio one more chance here to operate. That's definitely a low volume. I think I may have had the volume turned down. So here we go. One more time. Volume's turned up full now. $113 volts. That's pretty darn quiet. Okay, I gave it a chance. Well, I can only assume I've made some kind of mistake. Maybe I compounded it somehow with monkeying around here. But today is over, so tomorrow I will look into this. I have to just start troubleshooting my own work here. A little bit disappointing, but not to be too worried. Okay, well, thanks a lot for watching, and tomorrow we can carry on. See ya.